So preparing solutions is our theme. When you prepare a solution, the whole point is to know the concentration. Now, there's a couple terms that are used when you know the concentration. One would be a primary standard, and that's what we're going to learn how to make. Okay, a primary standard is when it's made up from a known mass of a pure substance. So you took a solid, you weighed it out, you put it in a known volume. Okay. Primary is like one step original. Okay. There are other techniques for figuring out solutions of known concentration. Okay. We're going to learn about titration analysis in our next few lessons. Okay. If you can figure out a solution concentration by any other method, you just call it a standard solution. Okay. It's only primary. It's only primary if you made it up yourself. Okay. So two definitions you need to be aware of. Okay. Primary standard, how do you make it up? What are the steps to, and we're talking about making it up precisely with 3, 4 significant figures. Okay. So you're going to need a beaker. You're going to end up collecting your solute in a beaker, and you're going to dissolve it in a beaker. Okay. Beakers aren't good for precise measurements, but they're nice for collecting things, transferring things, and in this case, dissolving our solute. We'll want to do in a beaker. We'll need a glass stirring rod to break up that solute, stir it to make sure it dissolves. We need to know the mass of the solute. We need a scale. The volumetric flask, which tends to be a curved piece of glassware, is where we get the very precise final volume. Now on my drawing on the board, the line didn't really come through for our volume. So every time a glass blower makes a shape out of a piece of glass, it's never going to be exactly the same. So you can't just have a machine go and easily throw these lines on. Okay? So that line has to be calibrated so that the bottom of the meniscus of the liquid, of the water, has to be right at that line. The liquid is going to stick to the sides of the glass, so the sides of the liquid are going to go up a bit, but the very bottom of the liquid is where we measure. Okay. I put volumetric pipettes on my list. We're not going to need them right now for the primary standard, but we're going to dilute our primary standard and use a volumetric pipette to transfer a volume out of our volumetric flask. So that will be used shortly. Okay? So they're a transferring device. They're long glass tubes that have a larger bulb in the middle, and that bulb will be an appropriate size for whatever volume you want to transfer. Okay? They put the milliliter volume printed on them, but most volumetric pipettes will do 2 decimal places. So even though that says 25 on the one I circled, it's actually going to be 25.00 milliliters. Okay, so 4 sig figs when we transfer a volume. So let's go through the steps. How do you make up a solution? You don't lose any. You keep a high degree of precision. So when you're making up a solution, you have to know how much do you want to make up. So what size volumetric flask do you have? And you can pick any number. Okay? Typical sizes might be 10, 25, 50, 250, 500. Okay? We have a 2-liter volumetric flask for when we need to make up a large amount of solution. So you're picking a volume that you can buy a volumetric flask for, and then you can pick pretty much any concentration you want within the realm of science. So you can't make up 1,000 moles per liter. It's not possible. So an example is maybe you have a 250 ml volumetric flask and you want to make a 0.5 mole per liter sodium chloride solution. So if you know your volume and you know your solute, you can calculate, the concentration of your solute. You can calculate how much solute you need. Okay, when you make up a primary standard, you need to know what mass to weigh out. So to figure out that mass of solid, we're going to have to do this in 2 steps. We can't get to mass right away. We're going to figure out how many moles we want in the whole thing of solute, and then using the molar mass of that pure solid, we can figure out what mass. I'm going to run through that calculation. So first, we want to know the moles, concentration times volume. We want half a mole per liter. And we just have to watch our units. We need to use volume units. So we want 250 milliliters. So mils going up to the base unit liters is divided by 1,000. I find students hate putting all these expensive significant figures. These are pricey. There's all these N zeros that this device is calibrated a volumetric flash to measure. So particularly in your lab books, I want to see those digits. They may end up rounding away at the end, but I want to see them. So 0.125 moles. So I have an extra sig fig. That concentration we could easily make at 5.000. It's easy to add more sig figs there. So what mass is this? Okay, there's no mole scale, so we need to know how heavy it is so we can weigh it. Mass is molar mass times moles. So this is salt, sodium chloride, 58.44 grams per mole for the 1 sodium and the 1 chloride from our data table, times our moles. And I get 7.3 grams. So the numbers I put in this question just had 2 sig figs, okay? But we can easily, I'm going to raise these. We could make a solution potentially to 5 sig figs on our concentration as long as we have a scale that can give us that many digits. You'll find it's not the glassware, it's going to be how many digits do you have on your scale that will limit your sig figs. Here and in most high schools, you have 2 decimal places on your scale. Most university scales have 4 decimal places. So if you could weigh out about 2 grams, 2.4693 grams, you can get 5 sig figs on your mass of solute without too much difficulty. They're very expensive scales, but it's not hard to use them. Okay? And the glassware can do 5 sig figs. You can get concentrations of 5 sig figs. So you would first weigh out about 7.3 grams. We've done the math. Now it's the steps. You're going to weigh out solid close to the required mass in a beaker tarred to 0 on the scale. You're going to put the beaker on the scale first. You're going to hit tar. You're going to remove the mass of that glass beaker, and then you can add your solute right into your beaker. Okay? And you'd want to be close to 7.3. Okay? Don't worry about putting an extra crystal in or out. If you're 7.2 or 7.4, you can always recalculate exactly what concentration you have. Okay? Make sure in your lab book, though, that you carefully write out exactly what you want to weigh. Okay? And record the sig figs of the scale that you're using. Now we're going to dissolve that solid right in the beaker before we transfer it to the volumetric flask. It's much easier to dissolve something in a beaker. You could heat it in the beaker if you needed to. You can use your stirring rod to break up the chunks. Okay. So don't transfer the solid yet. So I've dissolved solid in much less than the desired volume. So you always have to think of what size of total volume are you going to have. My rough guideline is to use approximately half of the total volume. So if you're going to use a 250 ml volumetric flask, you'd want to stay around no more than 125. That gives you lots of extra volume that you can rinse your equipment with. Okay? And this is totally a rough guideline. Okay? Some teachers might say a third, I say about a half. Okay? You cannot use 300 mils, because if you use 300 mils to dissolve it, there's no way you can fit that in a 250, and you got to throw everything out and start everything all over again. Once you've dissolved your solute, you can't see any pieces. It's a nice homogeneous solution. Now we want to start transferring. Okay? We're going to transfer that aqueous solution to the volumetric flask. Okay? When you're highly skilled, you can pour from the beaker down a stirring rod right into the volumetric flask. Okay? You want to pour down the glass stirring rod so you don't have any splashing. Okay? To make it a little easier, you could always use a funnel and pour into a funnel, and that can work also. Okay? And while you're learning, we'll give you funnels to pour into. The key thing here is we can't have any drops coming out of the beaker and falling on your lab bench. Everything needs to get transferred into that volumetric flask, be it down the stirring rod or a funnel. Your beaker now looks easy, but there's still residue sitting on the side of your beaker. So you're going to rinse that 2 or 3 times. Pour 5 or 6 mils in, give it a rinse, pour it back in. This is why we only use half the total volume in the beginning. Okay? Our rinses are small. We can do many of them. If you do 3 rinses and you still see a speck of something, you can use some more water and you can rinse it, distilled water. Okay? After you've rinsed your beaker out 3 times, there shouldn't be any solute left. It should be just pure distilled water in your beaker. Okay? You'd also want to be rinsing your funnel. As you rinse your beaker, your funnel's getting rinsed, and you can rinse your glass stirring rod in the process of those rinses. So you've now transferred all of the solute out of your beaker. You dissolved it, you rinsed it 3 times, you're very confident everything's out, and now you're going to fill up your volumetric flask. Whatever amount of water you need to get it up to that line. So you'd want to pour most of the volume you want fairly quickly, but you're going to want to use a medicine dropper to get those last few drops in. Okay? You're not going to be able to pour and get the bottom of the meniscus right at that line. An eyedropper, you can go drop by drop or even half a drop by half a drop at the end to be careful. Once you get to that line, you are done. Now you would want to shake up your volume, cap it and shake it up. I didn't type that out, but you're done all the steps. You have your solution. Okay. The shaking, just make sure it's all mixed up before you use it. Okay. So in high school science, this isn't something you do very often, but your lab tech or your teacher is doing this every day or every week to make up all those solutions that you use. It's a skill you need that you know how to make these up. Okay. It's something you'll learn in high school and maybe use in post-secondary. So let's practice at least the math part of making up a solution. Okay. So I'm going to ask you to calculate the mass of solute required to make a 0.0500 mole per liter lithium hydroxide solution with a total volume of 100. Okay. So I've summarized the two key pieces, the desired concentration, square brackets means concentration in chemistry, copied over the So to calculate the total mass, starting with moles, concentration times volume, .0500. So those leading zeros aren't significant. They're just placeholders, but the trailing two are significant digits. Times the volume, I've got 5 end measured zeros. So I have to keep all of those. So I end up with 0.00500 moles. So then we can get what we really need, which is our mass, molar mass times moles. Moles cancel, so we're getting our mass in grams, the default of most scales, and rounding to 3 sig figs, 121. I think I had 1195, I believe, and then rounded it. Okay. So in order to keep the 3 sig figs that are desired in the concentration, you're going to need a scale that does 3 decimal places. Our standard student use scales at ND are only to 2, but we do have a scale that goes to 3 that our lab tech can use or that I can use to get 3 decimal places and get the sig figs when we need them. So our last question is going to tie in our dissociation skills. What if you want to make a certain concentration, but not of the ionic compound, of the dissociated ion? Okay. We can't weigh out dissociated ions. You can't go and get a beaker of just chloride ions. You have to weigh out some ionic compound. Okay. So we're going to figure out what mass of ionic compound we need that's going to give us the ion count we want. Okay. And it's going to look something like this. Okay. I'm going to describe the steps, largely just do the math of how to make a 0.1 mole per liter chloride solution. Okay. So I want 0.1 mole per liter chloride ions, but they're going to come from magnesium chloride. We're going to have to weigh out magnesium chloride. And we want the total volume to be pretty small. We're going to use a tiny little 25 ml volumetric flask. When you're asked about the concentration of an ion, we're going to have to write out its dissociation equation and work back to the solid. Okay. So we write dissociation equations. We start with the compound, magnesium chloride. You put that in water. You put the solid into water. And it's going to break up. Now, I wrote MgCl fast, but that's not correct. Okay. And the problem with this question would be is if you didn't write out the dissociation equation and you go too fast and you just look at magnesium chloride, you may not notice we don't have a 1-to-1 ratio. Okay. Magnesium is 2+, chloride is minus, so magnesium chloride actually has 2 chloride ions in it. So when it dissociates, we get 2 Cl minus. Okay. So every mole we put in, of this, we're going to get double the chloride. But we're just going to figure out what magnesium chloride concentration do we need. This is our desired end goal, 0.1, and we'll figure out, okay, using some stoic, what's that concentration of magnesium chloride? It's either going to be a double or a half. We're going to have to think of which way we need to do the stoic. Let's see. So I want to know how much of the pure solid I want to weigh out in what volume. Okay? Because I can't weigh out chloride. There is no chloride bottle. That's why we're doing this step. So we require magnesium chloride, which is a 1. Our given in this layout is chloride. We know that concentration, so multiply by 1, divide by 2. So if we can make a 0.0500 mole per liter magnesium chloride concentration, it'll give us that 0.1 chloride that we wanted. Now this is just like the previous questions. Okay. We know our concentration of our solute. Step 1, get the moles, C times V, and we're doing this for the solute we can weigh out. So 0.0500 is the concentration of the solute that will double into our chloride, and 25 mils, but we need that in liters. Mils is up to liters is divided by 1,000. Now when I say up, I'm referring to page 3 in your Alberta data booklet that has all the prefix meanings, that have the bigger prefixes on the top. So I divide this by 1,000. So we almost have the mass, molar mass of our magnesium chloride, 92.21 for 1 magnesium and 2 chlorides, times our desired moles. Will tell us what we need to weigh out. And we get, coincidentally, 0.120 grams again. So we need a 3-digit scale. We weigh out this mass. It's going to dissociate, give us double the chloride, and we can weigh that out. Okay. We're not going to be able to use much water. This is going to be a little bit of a tedious making of our solution. We only want to make 25 mils. So when we put our solute in our beaker, okay, we're going to weigh out close to this, okay, but we're only going to want to put in about half of our 25 mils. So you're only going to want to put in 12 or 13 mils when you dissolve it, which only gives you another 12 or so mils that you can do your rinses with. So this would be really making something up that you have to be really careful with the total volume. So that's how you make up a solution. The next lesson will be how you dilute it. If you made up a primary standard, you can use pipettes and take a known volume out. Maybe you take 25 mils out and you put it in 100. If you take 25 mils out and you dilute it up to 100, 25 compared to 100 is a quarter, 25 and 100, so you'd have a quarter of the concentration. Okay? If you took 50 out and put in 100, that's like a half, you'd have half the concentration. Or if you take 10 out and put it in 100, it'd be 1/10 the concentration. Okay? So you can make up maybe 1 mole per liter and then dilute it. Take 10, put it in 100, and now you've got 0.1.